The third distinguished paper in this session is titled Synthesizing MILP Constraints for Efficient and Robust Optimization. It's by Jingbo Wang, Aarti Gupta, and Chao Wang from USC and Princeton. And Jingbo will give the talk.
Okay, thanks for the introduction. This is a joint work with Aarti from Princeton and Chao from USC. In this work, we propose a method for linearizing arbitrary logical combinations of linear arithmetic constraints, and which is very important for MILP. I will first explain what MILP is and why it is important. So MILP stands for Mixed Integer Linear Programming, which is consisting of the objective function together with a set of linear constraints. So here the word mixed means that some input x may be either integer or real value. MILP has a wide range of applications, including protein folding, resource distribution, path planning, and so on. There are also many high-performance tools for solving MILP problem, such as Groby and Cplex. Well, in theory, this problem can also be solved by SMT solvers, such as Z3 and CVC5. However, in practice, the specialized solvers are much more efficient. Just to give you a quick idea, here is a tiny instance of protein folding example. The Groby took less than a second, while Z3 took 18 seconds to finish. So what it shows is that for those MILP problem, it's better to use the specialized MILP solver. However, it is difficult to write those correct MILP solver because they are less expressive than SMT. For instance, if you are provided with a conjunction of linear constraints, you could directly use them because they are already in the linear format. However, what if you are provided with a Boolean constraint? Then you probably need to treat this Boolean variable as an integer and then rewrite this logical implication as a linear formula and also make sure they are still equivalent. So while the toy example on the previous slide still seems manageable, however, in practice, you may have to deal with more complicated constraints. For example, such as the implication, disjunction, interpret function, or maximum. So the existing approaches for handling those logical constraints using linear format have many limitations. The manual encoding is labor-intensive and error-prone, and the pattern matching such as a big M value, will make the output formula unnecessarily large, and it also has an unpredictable impact on its performance. So our idea here is to use program synthesis. Our method is based on SyGuS, so can we automatically synthesize a correct, equivalent, efficient, and robust MILP formula from arbitrary logical constraints? So now I have provided the background. Let's take a look at one motivating example. Imagine that you want to use MILP to encode this protein folding problem. So a protein is a chain of amino acids, which can be classified as hydrophilic and hydrophobic. So here, your objective is to maximize the number of matchings of those hydrophobic acids, which are represented by those blue circles. Based on the molecular biology, you have to satisfy the following three constraints in order to match a circle I with a circle J. So in order to encode those three constraints, decision variables Mij and Fk need to be introduced. So if there is a match between I and J, then Mij is true. Both of them are regarded as an interpreted function. So given those three descriptions, users can write their input constraints like this. And for example, in the first constraint, it just means that if there is a match, and then there must be an even number of circles between circle I and circle J. So now I will explain how our synthesis works. So given this input constraint in the SMT format, we first need to specify the domain-specific language, or DSL, which is used to construct the linear formula. And then we need to specify the synthesis instance. So here we are going to find a candidate psi that is equivalent to the input phi. And finally, we are going to run the synthesis algorithm, which is a guess and check procedure. And finally, we'll output its formula. So there are 3 challenges in this framework. First, the DSL must be expressive enough. It means that enough number of new decision variables and relations must be introduced. Otherwise, this DSL may not be expressive enough to capture the desired solution. And also, we don't want to add so many decision variables because it may enlarge the search space unnecessarily. Second, we also want to make the synthesis to be efficient. And third, if there is more than one solution, how can we pick the one with a higher quality? So this brings us to the third part of this talk, our method. So our method takes the SyGuS as baseline, and we proposed 3 innovative solutions to address the challenges we have mentioned before. So for the first challenge, we strengthen the DSL by iterative decomposition until the DSL is expressive enough to capture the candidate. So for challenge 2, we prune the infeasible candidates and prioritize the search space. And for challenge 3, we develop a convex hull-based splitting to pick a high-quality candidate. So these 3 components are our new contributions. Let's take a closer look at strengthening DSL. So given a Boolean operation such as the one shown on the protein folding example, you may want to add more decision variables to this. Otherwise, the DSL is not expressive enough to capture the equivalent linear format. So in this case, for A implies B, we may need to add some small decision variables, such as the small a and b, to replace the predicates before and after the implication, so that we could rewrite this implication as an inequation. Applying this idea to the input example, for instance, for phi1, we could introduce a new variable x to replace the blue box, and then rewrite phi1 as phi1 prime. Meanwhile, we also need to add phi x, because they are also carrying new information. Similarly, for phi2, we also need to introduce new variable y to replace this orange box, and z to replace this green box. And finally, we also need to update phi2 as phi2 prime. And the similar rewriting procedure also happens to phi3. Eventually, we are able to update our input specification and also our DSL by augmenting those newly created variables. And with those newly created variables, it would make the DSL expressive enough to capture the desired linear formula. And right now, with the updated input and the updated DSL, we are able to convert the old synthesis specification into a new one. Although the old one may not have a solution at all, the new one is guaranteed to be expressive enough to capture the candidate. And obviously, there are many ways of adding new variables. Some may be better than the others. Well, the right-hand side is better in such a case that by only adding 3 new variables, it would make the DSL expressive enough. And more importantly, the predicate for x is synthesized out of the blue because it does not exist in any of the original formula at all. That's why you can see that in the output linear formula, there is the newly created variable x colored in orange, and there are also some arithmetic computations over x. Here, we also want to highlight that there is one more solution psi without even using x, and I'm happy to talk about that offline. Now, let's move on to our second contribution, pruning the candidates. So our synthesis specification is to find the candidate psi that is equivalent to phi for all the possible inputs. To speed up the performance of the synthesizer, we propose a 3-phase approach, which is an under-approximation to guess a candidate and then check if it is valid. So for instance, the check procedure will falsify the equivalence in the smaller domain before falsifying them in a bigger domain. And only the candidate is verified in a small domain, they will be forwarded to the bigger domain. This effectively prune the search space. Now, finally, let's move on to our third contribution. So there are many candidates, each of which is a valid solution. However, some of them may have different impacts over the Gurubi solver's performance. So we really want to pick the one with a higher quality. For instance, there is an input formula phi, which is consisting of two formulas, and the blue region represents the solution space for this formula. We first synthesize our first solution, psi1, and as you can see, the orange area is the relaxation space for psi1, which means the convex relaxation from the original problem. And you can see that this orange area over-approximates the blue area too much, and it would lead to a longer solving time because Groovy typically searches solution in the orange area first, and then checks whether it belongs to blue area or not. So a smaller orange area is more likely to reduce the solving time. But why is psi1 not a good candidate? Because psi1 is synthesized from phi by treating each subformula independently. So it does not capture, it only captures the intraformula relation without capturing the interformula relation. So in order to capture the interformula relation, we need to split a variable x2 into two instances like x2k and x2 not k in order to capture this. So our convex hull-based splitting is used for this scenario. And by splitting x2 and x1, we are able to generate a new formula psi2 that is much better, and it has a much smaller orange area, which is more efficient to solve. Okay, let's see if our proposed method works in practice. We implemented our method by leveraging Rosette and Z3, and our benchmarks have three groups. The first group is a classic optimization benchmark from the operational research, while the second group are machine learning applications, and the third group are collected from the online Q&A forums where users have real trouble in writing those constraints online. And our experiments were designed to answer the following two research questions. First, what is the quality of the synthesized constraint? And also, how efficient is our synthesizer? So for RQ1, we plotted the MILP solving time. So here the solving time is with respect to the Groovy solver, and the solving time is having both synthesized and had written constraints. So as you can see, the blue bar and the orange bar are pretty close. And for 50% of the benchmarks, the difference between those two bars are very tiny. And also in general, our synthesized benchmark are having 9% performance speed up over the manually crafted constraints. We also compared the size of the synthesized constraints. It shows that the synthesized constraints are also very similar to the manually crafted constraints in terms of the size. And also, it is nearly as compact as a manually crafted one. So for RQ2, the efficiency of the synthesizer, we actually plotted the synthesis time for the real-world optimization benchmarks. So as you can see here, the synthesis time typically takes seconds to minutes. So it is quite efficient and much faster and more economical than recruiting a domain expert to manually write those constraints. Meanwhile, we also try to quantify the impacts of each individual components in our method. And it seems that strengthening DSL has a significant impact. It is because for 70% of the benchmarks, the initial DSL was not expressive enough, but after the decomposition, it would make the DSL expressive, so which is pretty nice. To summarize, we have proposed a new method for synthesizing correct and efficient and robust MILP constraints. And we have proposed 3 contributions, and the experiments show that it works well in practice. And that's all, and I'm happy to take any questions.
Hi, I'm Keyur from UIUC. My question was, for example, with the proteins, if you synthesize some constraints for one protein, will it also, is it for all proteins, or is it, are you generating one protein at a time?
Is it for all proteins? Because all the variables in that formula are symbolic, so you could instantiate with any number of acids in that protein, so it works for any proteins, not just for the example.
Okay. And you showed how, like, could it be possible that different synthesized constraints are better for different classes of proteins? Maybe you could get better performance out of that?
It depends on the constraint you are writing. If you just are having all the similar 3 constraints for your protein folding problem, then you could possibly just have one best solution for all of them because your constraints are already specified. But if you have a different protein folding problem with a different Boolean logical constraints, then yes, you may have a different linear best solution for your case.
Okay.
So
Thank
it
you.
Depends case by case.
Okay, thank you.
Hi, Jingbo. Thanks for your wonderful presentation. I'm Ray from University of Michigan. And my question is that for your code pruning and prioritization, you said that you first use under-approximation and you first verify those in small domain, right, to prune. So my question is that you still need to first generate all the possibilities, right? So would you consider like use some like guidance to avoid first generating all the possibilities so that you can prioritize your search?
Yes, we certainly consider that. So in our iterative decomposition, you know we introduce some new variables, right? So by conjuncting those new formulas with the original input, so you actually make this synthesis problem compositional. And then this is actually the problem structure we are leveraging. And then by using those compositional synthesis, we can greatly speed up. And this just one speed up we can get from leveraging the problem structure.
Okay, thank you so much.
So one more question. In traditional optimization, there's often these decomposition techniques like primal dual and so on. Does your DSL capture those kinds of techniques, or is that a next step?
So this kind of decomposition is not directly expressed in our DSL because our DSL is very basic. It's just expressing conjunction of linear formats. But the decomposition in some more complicated format, we could incorporate that in our future design of DSL. But right now, it's just a very basic format.
Great. Okay, let's thank Jingbo again.